let's do a couple of examples. First one just for exercise and to get a bit more familiar with Ito's rule. Suppose you want to compute the integral of w dw. Okay. So if you are doing standard calculus, then integral 0 to t of s squared d, sorry, not squared, s ds would be what? It would be t squared over 2 minus 0 squared over 2, so it's just t squared over 2. Okay. Well, so we would maybe guess that this should be something like w squared of t over 2. Except, maybe not, because there is this extra effect of second order terms. So in fact, what we are going to show is at the bottom of this slide. It's integral of w dw is going to be w squared of t over 2. That's this part that I was guessing. But there is an extra term, minus t over 2 when you divide by 2. Okay? And we will see that this term comes from Ito's rule. But the point is, we can, at least in this case, compute this stochastic integral. It looks like a kind of a strange animal, maybe not easy to compute, but actually it's not so hard to compute. So let's see how this works. Since we are guessing that this integral is connected to the square function, then let's try to apply Ito's rule on w squared. Okay? So my function f of x is x squared. The first derivative is 2x. The second derivative is 2. Okay? So I'm going to apply Ito's rule using these derivatives. And, well, I applied Ito's rule to dx. So x here is my w. So x was mu dt plus sigma dw. Well, I'm going to write dw as 0 times dt plus 1 times dw. That's just a way to write dw. So my mu is 0 and my sigma is 1. Right? My mu is 0, my sigma is 1. Let me write that down here for you. That's not the nicest way to write it. Mu is 0 in my Ito's rule formula, and my sigma is going to be 1, because I can write dw like this. Okay, so now I have my Ito's rule. I can just go back to Ito's rule, which is, let's say, which version I'm going to take. Maybe this version down here. Right? So first derivative with respect to time. Well, there was no time there. The derivative with respect to time was 0. Then the derivative with respect to x was 2x, or 2w dw. And then plus 1/2, second derivative was 2. So I'm going to have 2, 1/2 times 2 times sigma squared, but sigma squared is 1 dt. Okay? So that's what I'm going to do there. So dw squared is first derivative 2w dw plus 1/2 second derivative is 2 times sigma squared, which is 1 dt. Okay? Well, all right. But I mean, the meaning of this is really its integral when you integrate it. So which when you integrate, you are going to get w squared of t minus w squared of 0 equal to the integral of this from 0 to t. So 2w, I'm going to call the integration variable s, 2ws dws. And then I integrate this from 0 to t. Well, this is 1 times ds. So I don't write 1 here, but it's integral of 1 times ds. Fine. Well, what is this integral? Integral of 1 is just the variable itself. It would be t minus 0, so just t, right? So from here, this is just t. And if I move this to the other side, I get that twice my integral ws dws. This is 0, so it's w squared of t, and I move this to the other side, minus t. That's how I get this formula. Okay, so using Ito's rule, it's actually easy to compute this integral of w dw, and it's not quite the same as in Newton's calculus. There is this extra term coming from the second order effects of Brownian motion. That's our first example of using Ito's rule. And then let's do another one. Very important example, okay, because this is basically dealing with the Black-Scholes Merton model. I'm going to take a function which is exponential of a linear combination of a Brownian motion and time. So e to the a w of t plus bt. This is exactly how my stock will look like in the Black-Scholes Merton model. Okay? So y is really going to be the stock price in the benchmark continuous time model. Let's do Ito's rule on this process. So my function is exponential function of this type. I can think of y as a function of t and w of t, okay, where f of tx is exponential of ax plus b times t. And let's compute the derivatives. So the first derivative with respect to time, well, time is here. The derivative of the exponential function is just itself. So f, but then this b comes down, right? When I have to take a derivative of this exponent with respect to time, that's just b. So b comes down times the exponential is f. Similarly, the first derivative with respect to x, well, same thing. The derivative of the exponential function is itself, so it's f, but this a comes down, so I have a times f for f subscript x. And then I take another derivative to get f subscript xx, okay, the second derivative with respect to x. Well, that's just going to move another a down, right? If I take a derivative of f here, I know it's a times f, so I'm going to have a squared times f. I just take another derivative here, moves another a down. So I'll have a squared times f for the second derivative. All right? Well, then I can apply my Ito's rule. I'm not going to go back into the slides. I'll just try to remember it. So let me do the easier part first. Here we have the first derivative times sigma dw. Well, sigma is 1 because my x is just w. So dw is 0 dt plus 1 times dw. So there is no sigma. The first derivative is a times f. But f is actually y. So I'm going to write, instead of f, I'm going to write y. Okay? So the first derivative dw, and the first derivative is af, which is ay, because f is y. Here, I have the derivative with respect to time, which is bf, but that's by times dt. And then I have 1/2 second derivative with respect to x, which is a squared f, which is a squared y. So it's 1/2 a squared y. I factored out y. Okay, I get this. So if I tell you the Black-Scholes Merton model is this, that's equivalent to saying the dynamics of y behave like this. Or I can tell you the Black-Scholes Merton model looks like this, which really means that the stock price is like this. That's what we are going to do. Let me do one special case here, which is important, which is the case when I make this 0, when I make the dt term. So the dt term is called the drift of the process. When I make the drift equal to 0. Okay. What happens then? If this is 0, what kind of process is y? Well, then y is a martingale. If I make 0 the dt term, why is that? Well, think always in the integral form, integrated form, right? Then y would be equal to y of t would be equal to y of 0 plus integral of, in this case, a y of s dws. But a constant is a martingale plus integral dws is a martingale, so I have a martingale plus a martingale, which is a martingale. Right? So if I don't have the dt term, then such a process is a martingale, at least under some technical conditions, which we are going to assume. So if I make this 0, my y is going to be a martingale. Let me use that fact to get a nice formula that I will need later. So to make this 0, I'm going to make b equal to minus 1/2 a squared. All right, then this is 0. Okay, and then I'm going to substitute that b here. So my process y is e to the aw of t minus 1/2 a squared t. Just substitute this b here. So now I know that this process is a martingale. Okay, it's not so obvious, maybe not obvious at all. If you look at it, if I give you this process and tell you it's a martingale, well, why? Well, using Ito's rule, you see why, because the dt term is 0. And so this process can be written as an integral of itself times a dw, but integrals dw are martingales plus constant. All right. So let's just use the martingale property. The martingale property is expected value from the point of time s of y of t in the future is y of s. Let's just substitute for y. I have substituted this for y, and I'm going to move the deterministic part to the other side, so I can write that the conditional expectation with respect to time s of e aw of t is e aw of s, y of s, plus 1/2 a squared t minus s. Okay, I moved this t part to the right hand side from the left hand side. Okay, this is a very useful formula. It gives you a way to compute conditional expectations of the exponential function of Brownian motion times a constant at some future time t. Okay? So when you solve your homework assignments, problems in the homework or the exam, if you take the exam, it may be useful to remember this formula. Okay? We know how to compute conditional expectation of basically Black-Scholes price, price in the future given information up to time s. If you know about moment generating functions in probability theory, this is nothing else but a generalized moment generating function. So for a normal distribution, if I put s equal to 0, that's the definition of moment generating function. Is just an expected value of an exponential of constant times normal distribution, and then you would get exactly this with w of 0 here. So this would disappear because w of 0 is 0, and s would be 0 here. This would just give you the standard moment generating function formula. If you know about moment generating functions for normal distribution, if you don't, doesn't matter, it's included here. This is the formula to have in mind. Okay, so we did two things in this slide. We are able to do Ito's rule on an exponential of a linear combination of Brownian motion and time, which is going to be the stock price model for us later. And we know how to compute conditional expectations of such a process. Fine. And let me finally tell you about Ito's rule when you have more than one stock. Okay? There are options which are written which depend on the values of more than one variable, 2 stocks, 3 stocks, interest rates, whatever random variables you write your option on, your underlyings you write the option on. In this course, we are not going to do more than 2 random factors, so I'm going to give you here the 2-dimensional Ito's rule, but there is a similar version for 3-dimensional, n-dimensional, higher dimensions. So let's think about x and y as being 2 stocks. So the typical way to model this, and maybe they are not independent, maybe they are correlated stocks. So I'm going to have wx, which is going to be one Brownian motion, and wy, which is going to be another Brownian motion, and I want them to be correlated. And the way to model this, we say that they have a constant correlation rho if the expectation of wx t, wy, t is rho times t for every t. And you also write this in this way, that dwx, dwy is rho dt, which really means also not just expectation, but if you define quadratic covariation between these 2 processes, the quadratic covariation is rho t. Okay, so I have 2 stocks, mu x dt, sigma x dwx, mu y dt plus sigma y dwy. Ito's rule, again, if you know Taylor expansion for 2 variables, then you can do it like this. Okay, change in f, if it's an option price which depends on 2 stocks. I didn't put time here, but you can just add time too. Okay, if I have 2 stocks, it would be change in the option price, change in f, df is fx dx plus fy dy. These are first order terms in the Taylor's expansion. And then second order terms, 1/2 fxx dx squared plus 1/2 fyy dy squared, partial derivatives with respect to y, second one, plus second order mixed partial derivative fxy dx dy. All right, so that's the formula for 2 variables. Okay, when the second variable is time, then these 2 last terms disappear, because time and dt squared is 0 and dx dt is also 0. But if y has non-trivial random component, if sigma y is not 0, then you get these 2 terms. And then you can just, we don't even have to look carefully at this last equation, just to know that now using those informal rules, that dw squared is dt, dw is 0, dt squared is 0, and including this rule for correlated Brownian motions, dwx, dwy is rho dt, if you just use those rules and substitute dx and dy here, you can get the correct formula, which is here. I'm going to go in detail through it, but you can get it. Most of the time, I will need this formula in a very special case, when my function is just a product function. So product rule, d of x times y. Right, so the first derivative with respect to x is just y dx. Here it will be x dy. Okay, so if I use this formula, I'm going to get, from these 2 terms, I'm going to get x dy plus y dx. By the way, this is exactly your differentiation of the product in the usual Newton's calculus, right? The derivative of the product is the first function times the derivative of the second plus the second times the derivative of the first. So this is the usual product rule in differentiation of deterministic functions. Then the second derivatives are 0, because these are linear in x, linear in y. These second derivatives are 0, so the only other term that survives is this one. And so you have sigma x, sigma y rho, and this mixed derivative first with respect to x, then with respect to y, you just get 1, right? So this mixed derivative is 1, so you just get rho sigma x, sigma y dt. Okay? So this is a useful formula to know. We will need it a lot. Derivative or dynamics of a product of two Ito processes of this type. For example, when we when we discount or where we change from euros to dollars and multiply by exchange rate, we will be multiplying, and then we need a product rule. Right. So maybe this is a little bit boring, a lot of formulas, but this is the main mathematical tool to do everything else in the course. We have to know it. You will have homework assignments to practice it. The bottom line is there are these formulas for a function of time and of a Ito type process, or more than one Ito type process, and you can find these formulas in the slides or wherever you can find them, and we will learn how to use them in pricing options. All right, that's it for now.